For this video, we want to start talking about the graphs of quadratic functions. Specifically, we'll start looking at some of the features of a graph, such as its vertex, axis of symmetry, and whether that graph has any maximum or minimum values. We'll also take a look at how these, you can actually look at the equation itself, find these key things, and actually come up with a graph on your own. So one of the first things you want to know about the graph of a quadratic function is that its basic shape is known as a parabola. So kind of a U-shaped graph. And if you look at one of these U-shaped graphs, you'll notice that it has symmetry, that you could fold it right up the middle and it'd match up with itself. This line where you could fold it and it has symmetry is known as the axis of symmetry. Now it is good to know where the axis of symmetry is, because wherever that axis and the graph itself meet, you get a point known as the vertex. So in the example on the left, the vertex is located right at the bottom of the parabola. Now these parabolas could be facing up or they could actually be facing down. No matter which way they're facing, they still have an imaginary line up the middle that you could fold them, known as the axis of symmetry. And again, wherever that axis, say, crosses the graph, you would get a vertex. Let's do some really quick examples to make sure you have that concept down. So here I have the graph of a parabola. Where would you say is the axis of symmetry? Now if you're looking at that -5, you're close. It does have to do with the -5, but remember that the axis of symmetry is a line. So describe it using the notation of a line, and the axis of symmetry would be at x equals -5. As for the vertex, we'd signify that using a point. So at the point -5, 0, that's where the vertex is. Okay? Let's give this a try with another example. Where would you say the axis of symmetry is for this parabola? Well, you can see that you could fold it along the line x equals 4. And so that is its axis of symmetry. Now where the line x equals 4 crosses the graph way up there at 4, 9, that would be the vertex. So just like that. Now if you know the basic shape of a quadratic function, the parabola, you can use your techniques of transformations in order to come up with new graphs. The key is figuring out which parameters in here give you the different stretches and shrinks, and which ones actually shift the graph. So if you take your quadratic function and write it in this form, f of x equals a times x minus h, the quantity squared plus k, the a gives you your reflections and also tells you if it's been stretched out in any way. The h will give you a shift horizontally, so left or right. And the k will give you a shift vertically. Now, how that really boils down in practice is using the h and k, you can figure out where the vertex is located. And then using the value of a, you can figure out whether your parabola is facing up or down. And then again, by looking at the value of a, you can see whether it needs to be narrow or fairly wide, depending on if any stretches have happened. Let's use this idea to see if we can graph f of x equals -2 times x plus 4, the quantity squared, plus 5. The first thing I'm going to do is look for those shifts. Notice how inside parentheses I have an x plus 4. So that tells me my parabola is shifting to the left 4 units. And remember, when we have a transformation on the inside, it definitely goes left. So it works kind of the opposite as what we think it should. Now with the plus 5, that is also a shift, but that is a shift up. So that gives us the location of the new vertex. The vertex of this particular parabola is at a -4, +5. Okay, that's pretty good. At least we have 1 point on our graph. Now, we also need to put the rest of the parabola, and we'll use the value of a, that's the -2 out front, to determine a little bit more. Since the a value is negative, a -2, we know that this parabola is actually facing downwards. Now, also since it's 2, it's been stretched, so it's a vertical stretch, and should be narrower than your normal parabola. If you want to get really down to exactly how stretched it is, you could imagine plugging in a few different values for x and plotting them out, so using like a scatter plot. And then visually you can see that yes, it has been stretched out just a little bit. So this parabola here represents our function. Let's try and do this entire process backwards as well. In other words, what if we have the graph of a parabola, can we work backwards to actually create what the function is? Well, one of the first things we want to figure out is how has this new graph been shifted from the original one? In other words, where's the vertex, and where did it get moved to? Well, this particular graph here has a vertex at 4, 1. And so I know how much it's been shifted to the right and that it's been shifted up. So I could start off my function like this, that f of x is equal to a times the quantity x minus 4 squared plus 1. Now notice how I haven't put anything in for a yet. That's because a determines the direction by its sign, and it also determines whether it's been stretched or shrunk in some sort of way. And right now, just by looking at it, I'm not sure if it has. Well, just from the direction of the graph, I do know that a needs to be a positive number since it's facing up. And so what I really need to figure out is, okay, has it been stretched? Because this parabola does look like it's a little bit wider than normal. Well, in order to figure out, I'm going to use another point on this graph. So I've picked out the point 2, 2. Looks like it definitely goes through there. And I'm going to plug in 2, 2 into the x and into the y of the equation. Now by doing that, I can actually solve for a to see if it has been stretched or shrunk in some sort of way. So in solving for a, I get that a is equal to 1/4. And then I can put this back into my entire equation and get that this graph comes from f of x equals 1/4 times the quantity x minus 4 squared plus 1. And now that I can see that since the a is the 1/4, that it's actually been shrunk in the vertical direction. As you can see, it's really important to figure out where the new vertex is by looking for those stretches and looking for those shifts to see what happens. Now, unfortunately, that special form that we had these functions written in is not always how a quadratic function comes. After all, when we were in the solving section, we saw many quadratic functions that were written in standard form. Well, in order to still figure out, say, what the shifts are, you have to end up rewriting this into the other form. And in order to go through that process, you have to use completing the square. Now, once you use completing the square, then you can actually see your stretches and shifts and determine what the graph should look like. So we're going to try this with a couple of examples. So let's take a look at f of x equals 4x squared minus 4x plus 21. Because maybe this is some sort of function I want to graph, but I'm not really sure where the vertex is. So in order to do this, I need to put it into standard form. Okay? So what I need to do is go through the process of completing the square. Okay, here's how that works. I'm first going to replace that f of x with just a y, just so it's a little bit easier to keep track of. Then in the first step, I look at all my terms that contain an x and I keep them on one side. With the 21, since it does not contain an x, I'll put it on the left side by subtracting a 21. Now you want to check your x squared term and see if it has any coefficient out front. This one has a 4, so 4x squared. Well, we're going to divide everything through by 4. All right, a little bit better. And now we want to start to see if we can make our magic number that will make this factor much nicer. Remember to check your linear term for this one, so the negative x. So we're going to take negative 1 divided by 2 and square it. This will give us a value of 1/4. So the 1/4 is our magic number that we need to add to both sides. Now the whole reason for adding the 1/4 is so that it will factor nicely on the right. On the left side, we do got a lot of junk piling up, and it simplifies a little bit when you combine those two fractions. But for now, really focus on the right side. That x minus 1/2 quantity squared is what it factors down into. Alright, so we're almost home free. And the last part is to really start moving things back onto the right side. So work to get y all alone. This means that we'll have to, say, multiply by 4 and then add 20. So in this way, we get our function f of x equals 4 times the quantity x minus 1/2 squared plus 20. And then when it's written in this form, I can see that it looks like it's been shifted to the right 1/2 and it's been shifted up 20. Also, the 4, since it's positive, tells me the parabola is facing up and that it is narrower than a normal parabola. It's actually had a vertical stretch to it. So you can see that completing the square is really handy in order to put this in a much nicer form. Now remember that the downside with using completing the square is that it has a lot of steps and that it's not always quite very clean. For this next example, watch how it gets a little bit messier and I have to really be careful on what I do with my fractions. This one starts off with f of x equals negative 1/3 x squared plus 3x minus 6. For this one, I start off by, again, switching out the f of x with a y, and then shuffling things around a little bit so that my x is on the right, and I put the 6 on the other side by adding 6 to both sides. All right, that looks pretty good. Now this one has a negative 1/3 out front. So I need to divide both sides by a negative 1/3. Well, if I divide by a negative 1/3, that's the same as multiplying by negative 3. So I'll do that instead. That sounds like a little bit cleaner way to go. All right. Well, now that we have this, we can start working to find that magic number. Remember to take the negative 9, divide it by 2, and square it. This will give you 81/4. And so that number we need to add to both sides of our equation. Now again, the left side will start to get a little bit messy, but try and focus on the right side where things will factor nicely. In fact, the right side factors down into x minus 9/2. Now notice where those numbers are coming, like the x minus 9/2. You found the minus 9/2 before by taking negative 9 and dividing it by 2. All right, so the last part of this is really to start shuffling things back to the right side. So work on getting y all alone. And this one involves a bunch more things that you can simplify. So I've cut out some of those steps. But when you do shuffle things back to the right side, you get f of x equals a negative 1/3 times x minus 9/2, the quantity squared, plus a 3/4. And so again, when it's written in this form, you can see the different shifts. That it's been moved to the right 9/2, and that it's been moved up 3/4. And that since this has a negative 1/3, the parabola is actually facing down and is a little bit wider than normal. Now, just like last time, you might be a little bit curious as to finding out ways you can avoid using completing the square. After all, with all of those steps, you can see it can get very messy very quickly. Well, fortunately, there is another formula that can really help you out that will find the vertex. And so the way this works out is if you know that your function is in the form ax squared plus bx plus c, the vertex is located at negative b over 2a, f of x of negative b over 2a. So the way you want to start reading this is that this is giving the location of the vertex. The x-coordinate of that vertex is at negative b over 2a. And then to find the y value of that vertex, well, take your x and just plug it into the function and see what you get. And that's basically how this works. So let's give it a try in another example to watch this in action. In this example, I want to figure out whether f of x equals minus x squared plus 2x plus 5 has a maximum or a minimum. Now remember where the vertex is located. It's either at the top of the parabola or at the bottom, depending on which way it's facing. So in a sense, if we know the vertex, we know the maximum or the minimum. Well, rather than going through the process of completing the square on this one, I'm going to use my formula to help out. And remember that formula is negative b over 2a. So by plugging in the values of b and a, I can find that x is equal to a 1. Now remember, that's not the maximum or the minimum. That's merely just the x value of where the maximum or the minimum occurs, or just, the x-coordinate of our vertex. In order to figure out the entire vertex, I need the y-coordinate. So take this x value and plug it back into the function to see what you get. Well, when you plug it in, you get 6. Now, when you have both halves, now you can say whether you have a maximum or minimum. So what we have right now is that the vertex is located at 1, 6. Now, how do you know whether this vertex really is the max or min, though? Well, that actually comes from the value of a, the number in front of x squared. So since this is a negative x squared, our parabola is facing down. And since it is facing down, it means the vertex is located at a maximum, or the highest point. So in summary, we can say that the vertex 1, 6 is definitely a maximum.